Welcome. In this video, we will take a look at some related rates involving a circle. So the question asks, a thin sheet of ice is in the form of a circle. If the ice is melting in such a way that the area of the sheet is decreasing by 0.5 meters squared per second, at what rate is the radius decreasing when the area of the sheet is 12 meters squared? Okay, so if I think about related rates for a moment, there's really three components that are going to be in play here. There's going to be really two rates that we need to relate, and an equation that relates those two quantities. So in this case, let's start with the equation that would relate these two rates involved. We have the rate of the area of this circle, that's given in the problem. And then we have the rate that we want, which is the rate of change of our radius. So let's consider the equation first. The equation we can consider is just the area of a circle involving the radius. So the equation we could say is the area is equal to the radius squared times pi, or pi r squared, either way. And then I can consider, well, what are the two rates involved? Well, I have the area, the rate of the area change, and the rate of the radiuses change over time. So this would be the dA dt, that's the rate of the radius, or the rate of the area over time. And then we have the dr dt, that's the rate of change of our radius of our circle over time. So we would like to, in other words, relate these two items, those two rates, with this bridge called our area equation. So to be able to relate those two rates, I need to find them in terms of that equation. And so we're going to try to take the derivative with respect to time of this connecting equation. So we're going to consider here, take the derivative with respect to time, dr dt, of both sides. So we're going to be using some implicit differentiation here on both sides. So if I take the derivative with respect to t of the a variable, that's just going to give me dA dt. On the right side, we have a constant, that's pi, that will remain as just a constant pi. And if I take the derivative with respect to time of an r variable, r squared, we'll first get the outer derivative, that's 2r, times the derivative of r itself, so that's the inner function, would be dr dt. So that's the chain rule in effect there. The outer derivative is the 2r, and the inner derivative, taking the rate of change of r, is dr dt. So we'll see this is our equation involving both of the rates, dA dt and dr dt. So the area, rate of change of the area and the rate of change of the radius. So let's now consider what components we know. We know dA dt, the rate of change of our area, is decreasing at 0.5 meters squared per second. That's in our problem statement. So we can fill that in right away. So this is going to be negative 0.5, and this will be meters squared per second, is equal to, we have pi times 2r, the radius length right now, we don't actually know, but we do know the area of that circle at this time. So if I know the area, we know, again, area is equal to r pi r squared. So we can consider the area is 12. We want to go out and find the radius at this area level. If we do a little bit of work on the side here, we can say this is 12 divided by pi. And then if we take a square root of both sides here, we can get that r is equal to plus or minus the square root of 12 over pi. But here we're going to be working with positive distances, so we can simply use the positive version of that square root in for our r variable. So we'll take this guy right here, the positive root, as the r quantity. So we'll take this as square root of 12 over the square root of pi. And now the only piece that is remaining here is the dr dt, and that's the rate of change of our radius, and that is something we want to solve for. So dr dt, this is the variable I want to go out and solve for. And another unit calculation here, we know this radius here is in meters, so just remember that's in meters. We're going to be dividing by that meters. So we can rearrange this equation just slightly to find dr dt. We know this is negative 0.5 meters squared per second. Divide by, we have 2 pi, and dividing by the square root of 12, square root of pi, and that's in meters. And notice that when we take a look at the units of dr dt, just to make sure this is lined up right, notice that our units here with the meters will cancel out with one of those meters. And so our final units of dr dt is meters per second. Meters per second. And that makes sense because the radius is a linear measurement, and so it should have only one unit of measure, meters, and then per second for the time. So if we go and put this left side into our calculator, we can round this off to a few decimal points. This will be a negative rate, so it will be decreasing in size. So dr dt, to finish this off, is going to be equal to negative 0.0407. And this will be, again, in meters per second. So this is telling us how fast the radius is decreasing in size. At the moment in time, the circle reaches 12 meters squared. So I hope this is helpful working through a related rates with a circle. Take a look at the other videos in this playlist if you'd like to see some more examples.